All right, let's just dive right into this explainer. Today, we're looking at a brand new paper by Philip Dorau and Albert Much. And honestly, it reads less like dense theoretical physics and a lot more like a gripping detective story about the very nature of reality. We're going to explore a profound new way of understanding how the universe is stitched together at the most fundamental level.
But before we get bogged down in heavy quantum field theory, we've got to ask the ultimate question that this research is actually trying to answer. If we look closely enough at the fabric of empty space, does gravity as an independent fundamental force actually exist? Or is it just an illusion, an emergent property created by the shifting around of quantum information? I know, it sounds like pure science fiction, but this is the exact, literal problem this paper tackles head-on.
And that brings us to the core claim of the paper, which really lays out the massive stakes here. Quote, "The semiclassical Einstein equations follow from quantum relative entropy and its proportionality to an area variation." In plain English, the authors are arguing that the curvature of spacetime, the literal thing keeping your feet glued to the floor right now, comes directly from the measurement of quantum information. So let's unpack exactly how they arrived at this mind-bending realization.
Part 1. The Mystery of Gravity, the Missing Link. To really set the stage here, we need to understand why physicists are so desperate for a bridge between two totally different worlds. On one hand, general relativity beautifully explains how heavy objects curve space on a massive scale. On the other, quantum field theory flawlessly explains particles and forces on a microscopic scale. But the two rulebooks famously, stubbornly refuse to play nicely together. Figuring out how tiny quantum vacuum fluctuations actually interact with the grand geometry of space has been a monumental headache for decades. Physics desperately needs a bridge, what they call semiclassical gravity. But finding the exact nuts and bolts mechanism for how gravity emerges from the quantum realm, that's remained a totally unsolved mystery.
Which brings us to Part 2, Jacobson's thermodynamic twist, the first clue.
If we follow the historical breadcrumbs, it's pretty wild to see how physicists slowly realized that gravity behaves suspiciously like thermodynamics. Back in 1973, Bekenstein and Hawking showed that black holes have an entropy that's proportional to their surface area. Right after that, in the mid-70s, Hawking and Unruh discovered that accelerating observers actually experience totally empty space as a warm bath of particles. All of this built up to 1995, when Ted Jacobson made an absolutely massive leap. He managed to derive the Einstein equations purely from thermodynamic heat fluxes. He essentially showed that gravity acts exactly like the laws of thermodynamics applied to the fabric of spacetime itself. A huge breakthrough, right?
Well, hold that thought. Part 3, the quantum entropy problem, the fatal flaw. Because Jacobson's brilliant clue quickly hit a massive fatal roadblock. See, if you tried to measure the standard quantum entropy of a local region of space, the mathematics practically explode in your face. Why? Because microscopic empty space isn't actually empty. It's boiling over with violent vacuum fluctuations. This creates what physicists call infinite ultraviolet divergences, basically mathematical infinities that make our standard measurement tools completely useless.
So we have a stark contrast in how to approach the math. The old way, relying on von Neumann entropy, is completely broken in this context. Because of those infinite entanglements across the boundary of any space you try to measure, it's just ill-defined. But the new method? Quantum relative entropy. This approach remains perfectly well-defined and strictly finite, even amidst all that chaos of quantum vacuum fluctuations. It acts like the perfect mathematical scalpel to finally dissect this problem.
Part 4. Enter relative entropy, the missing key. To bypass all those nasty infinities, Dorau and Much turned to a core concept from quantum information theory. Instead of trying to measure the total entropy of a system, which gives you those mathematical explosions, they just measure the difference. Think of relative entropy simply as a measure of distinguishability. It asks one question: how different is a totally empty vacuum state from a state that has just a tiny coherent bit of matter passing through it? It's literally measuring the entanglement deficit. It just looks at how much information changes when you drop a tiny speck of matter into the void.
And the mathematics here are absolutely stunning. By invoking the Araki-Uhlmann formula, the authors elegantly show that this relative entropy, this purely informational difference between empty space and slightly less empty space, actually links directly to an excess of energy. It mathematically proves that information and energy are fundamentally inextricably linked.
Part 5. Energy, Area, and Horizons, Setting the Physical Stage.
Okay, we have the math, but where does this drama actually take place in the physical universe? Well, by using the equivalence principle, the authors zoom in on a tiny, locally flat region of space. Imagine you have a uniformly accelerating observer in this microscopic patch. To that observer, a boundary forms, a horizon that they cannot see past, known as a local Rindler horizon, or a bifurcated killing horizon. This specific horizon acts as the microscopic stage for our entire thermodynamic drama. It's the exact boundary where these invisible quantum energy fluxes actually cross. To really ground this concept, picture the abstract planes of this local horizon. These boundaries intersect, forming localized geometric wedge regions in spacetime. If you track our accelerating observer moving through time, an X-shape, a geometric cross, is formed. And right at the center of that cross, right in the middle of those mathematical axes, is where the magic happens. Right at that intersection is the bifurcation surface, usually labeled as S. What the paper proves, using rigorous quantum field theory, is that the local Rindler horizon is the exact stage where the energy flux, which, remember, we quantified by relative entropy, crosses that surface. The math shows that the flow of quantum information perfectly equals the flow of energy passing right through that point.
Part 6, Gravity from Quantum Information, the resolution.
All right, we've gathered all our clues, now it's time to snap them together. Let's walk through this cascading logic step by step and see how quantum distinguishability literally bends space. Step 1. We just established that relative entropy explicitly equals the energy flux across the local horizon. Step 2. This crossing energy flux physically causes a variation in the horizon's surface area. Step 3. Through the geometric focusing of null geodesics, that specific variation in area mathematically equals local spacetime curvature, which gives us the Einstein equations. So you start with a change in quantum information and you end up with gravity. This right here is the mic drop moment of the paper. They have successfully proven that Ted Jacobson's thermodynamic equations can be derived entirely within the rigorous framework of quantum field theory. Quote, semiclassical Einstein equations and thus local space-time curvature can be interpreted as arising from quantum information, namely the distinguishability between vacuum and excited states on local horizons. They've essentially shown that the curvature of space-time isn't some separate mystical force. It fundamentally arises from the simple ability to distinguish between empty space and slightly excited space on a microscopic horizon.
As we wrap up this explainer, I want to leave you with a genuinely mind-bending thought about the true nature of our universe. If this mathematical framework holds true, gravity isn't a fundamental force pulling you down. Instead, the curvature of space is just a macroscopic symptom of an underlying reality where the universe is constantly processing quantum information. So, is the empty space around us really just a massive invisible web of data? The space between your screen and your eyes right now might just be pure information. It's a lot to process, I know. Thanks for joining me on this deep dive, and as always, keep questioning the reality around you.